at the stomach. And for the record, if you guys want to visit this lecture, it's up on Canvas. We recorded everything from stomach all the way up to small intestine. But if you want to hear the lecture live, come to class. So stomach. So the presence of the stomach, when we look at the shape of the organ itself, is J-shaped, simply because it's the shape of a J. And what's present, what's particular about the stomach is the presence, or actually let's even talk about the function of the stomach. What exactly is the stomach for? It's for the storage of food. Whatever we've just consumed and ingested and has been propulsed down the esophagus has made its way into the stomach, where we've got a container, which is actually a fairly small container. It's about 50 milliliters in size. It's about 2 ounces worth. It's about 2 shots worth, and fairly compact. And it allows for distension, about 15 times its size. It can now expand quite a bit. And in the stomach, what you'll notice about the mucosae is the muscularis mucosae on the inside, that the layer within the mucosae are quite folded. And that folds that are present are called rugae. So that allows that distension from, that allows the expansion of the stomach. So in essence, a closed stomach or an empty stomach is quite wrinkled. And in order for that to distend or expand, that's where the rugae allows the expansion of it. So if you were to take a look at, like, for instance, I don't know if you guys ever look at a pug's face and see how how wrinkled it is, and you stretch it out. That's exactly what the stomach looks like. Another thing to think about, this is something that I'm quite guilty of, especially during Thanksgiving, is the effect of ventilation on stomach positions. If you ever notice, after eating a fairly heavy meal, you can't breathe. Yeah. Why is that?
Because you eat too much?
Of course you eat too much. That's partly it. But looking at the position of where the stomach is, the esophagus, right in the diaphragm, you have a little area called the esophageal hiatus. It's basically nestled in where the esophagus can travel through the hiatus and to make its way into the stomach. So above the stomach, just superior to the stomach, is the diaphragm. And what did we learn about inspiration? Inspiration involves the contraction of the diaphragm. So it moves posteriorly. So contraction of the diaphragm pushes down on the stomach. Now, when the stomach fills up, you're going to increase the amount of abdominal pressure. At the same time, with inspiration, you're trying to push down on something that's already quite a bit of pressure. So this issue isn't so much of an issue in healthy patients, but it's a particular issue for those that have respiratory issues. They mentioned don't have heavy meals because it's going to be harder for you to breathe. Now, looking at the rugae, you'll see this is an endoscope. And in this endoscope, they're basically going into the stomach itself. You can see the presence of the rugae. If I can just play that for you. They're making their way in. You can see all the wrinkles. Great. Now, what are the functions of it? Like I said, a food reservoir, about 50 milliliters when empty, and about a liter at capacity. So you can see how much we can expand that stomach. What do we do when we're with that food reservoir? We have, again, a bunch of gastric juices, which is going to be a bunch of water, at the same time also a bunch of enzymes, and a lot of protons, our hydrogen ions, that are all going to mix together. So we get the boluses of food that are dumping into the stomach, and then we're going to allow this mixing that takes place of the gastric juices along with the boluses of food. So here we're going to involve, again, peristaltic movements within the muscularis layer that creates these mixing waves. Basically, this is your stomach sort of churning every 15 to 25 seconds to allow mixing of the gastric juices with the food you've just ingested. So in this process where you get this mixing, You're mixing the enzymes to allow chemical digestion to take place, and then you get the physical, the mechanical digestion of that mixing of the food through the peristalsis, and the solution that we end up with is called chyme. So chyme is gastric juice plus the food, plus the ingested boluses. With that, in this process that we'll learn about is what's causing the stomach to expand with the filling of that food. Just like we learned in the Herring-Brewer reflex in the lungs, we also have stretch receptors in the stomach. So as the stomach stretches, you're going to learn that the stretch receptors are going to pick that up, and they're also going to start circulating hormones, which you'll learn later on. That's going to lend itself back to the central nervous system to tell you you're full. So those are the feelings of what's called satiety. Satiety is the feeling of fullness. And these are going to produce signals to stop eating. What's particular about the muscularis layer on the stomach is that I've talked about two different layers. I've talked about the circular layer, and I've also talked about the longitudinal layer. There's actually a third layer called the oblique layer, and that's present in the stomach as well, in the muscularis layer, to allow additional digestion from taking, to allow digestion to take place. And so you can see that present. You'll see the outer layer, which is the longitudinal layer, and that again runs along the entire length of the alimentary canal. You'll see the circular layer, which is just wrapping around the tube, and then the oblique layer that wraps diagonally. And that contributes to those mixing waves within the stomach. The different regions of the stomach, you'll see the cardia, which is up at the towards by the esophageal sphincter. Again, an area that's prone to inflammation, close to the esophageal sphincter. You get the fundus, which is the very top. Typically, the fundus area is more the reservoir area that fills up. The area that actually does fill up quite a bit would be the pylorus, which is by the pyloric sphincter below, where the small intestine starts. So pylorus, and then the body, which is going to be right up above. So as we fill up with food right down, as the stomach starts to fill up with chyme, you'll see most of it is within the pylorus itself. I've got slides of that at the very end of the stomach. I'll show you. So with that, you'll see the pylorus. What's technically happening in the stomach is to squeeze small amounts of chyme into the small intestine. So there's some squirting going on where the contractions of the pylorus is going to squeeze little bits in conjunction with the pyloric sphincter, which is going to allow little bits of chyme to make its way down the small intestine. So this process starts the process at which we're slowing down through the small intestine. And again, a pH of 2 and a pH of 7. And we're going to learn where the pancreas is going to be involved in dumping a bunch of secretin to buffer that chyme that makes its way in. More to come on that on Tuesday. So in that process, that emptying is called gastric emptying. And we'll talk about the rates of gastric emptying later on. Take a histological slide. Again, you'll see the presence of, again, the mucosal layer, the submucosa, which is going to contain the arteries and the veins and the nerves, and then the three different layers of the muscularis. Again, longitudinal being the outermost. You'll see the circularis, the circular muscles, as well as the obliques. Now, looking at the mucosal layer, again, the presence of rugae, the wrinkles. Within the rugae, you'll see the reason for those wrinkles are going to create these little pockets. And these pockets within the rugae are going to be the presence of exocrine or secretory cells. So not only exocrine, but also endocrine cells. So within these pockets, you're going to have these specialized epithelial cells that are going to have very specific functions. And those functions, which you'll learn later on, are the production of our acids, as well as mucus. These are these little gastric pits at the very bottom are going to have the gastric glands. So looking at these specialized cells, we have both exocrine and endocrine. We'll take first look at our exocrine cells. Why are they called exocrine? Because exocrine, again, remember, is dumping into the external environment. And given that the lumen of the stomach is the external environment, we're dumping things from within these cells into the gastric pits, which will make its way out into the lumen. So they are exocrine in nature. And the three that we'll talk about are mucous neck cells, and mucous neck cells are the ones up towards, I have that on the next slide over, are mucous neck cells, which are prominent towards, more towards the top of the gastric pit. You also have surface mucus cells, which are up at the very top. The mucous neck cells, we have our parietal cells, and then we have our chief cells. Parietal cells are going to be the ones that produce what's called an intrinsic factor. And that intrinsic factor we'll talk a little bit about later on. But the main idea behind parietal cells is that they produce hydrochloric acid. HCl. So combine those protons with chloride anions, and you get hydrochloric acid. Now chief cells are going to be secreting a protease. ACE being an enzyme, protease referring to an enzyme that breaks down protein. And the first one that's called is pepsinogen. Pepsinogen, which we'll learn in just a little bit. Pepsinogen is the inactivated form. And by the time it makes its way into the high pH, or I'm sorry, low pH, a pH of 2, becomes pepsin. So we go from the inactivated term, so ogen, anything that ends in ogen is the inactivated. Okay. Inactivated, and then active enzyme will be pepsin. Okay. If you remember angiotensinogen and angiotensin, again, angiotensinogen being the inactive form, angiotensin being the active form, same thing here. One way of remembering the chief cells for the production of the protein enzyme pepsinogen is something that's taught in med school, is chief cells, looks like chef cells. And chef cuts the meat. The other thing that's also produced by chief cells are gastric lipase. So this is different than the lingual lipase. Lingual lipase is produced by the tongue. Gastric lipase is produced by the chief cells. And both lipases serve the function of breaking apart fats. So the two enzymes, the two lipases, lingual lipase as well as gastric lipase, work to break down fats in the stomach. Again, due to the pH of 2. Now the other endocrine cells would be called G cells. So this is the, and not a term you really need to know, but enteroendocrine. So an enteroendocrinologist focus specifically on the endocrine cells within the stomach. And this are produced by G cells. G cells that produce gastrin. And gastrins are going to be the cells that we'll learn later on are going to promote the production of hydrochloric acid as well as the other exocrine cells. So in essence, these cells trigger localized production of hydrochloric acid by the parietal cells as well as pepsinogen and gastric lipase by the chief cells. They're the ones communicating to those exocrine cells saying, start producing stuff. You've got food entering the stomach. I need you guys to start producing a bunch of hydrochloric acid as well as the chief cells. And more to learn about that in just a minute. So why is that relevant? Well, you'll learn it is involved in the stomach. We'll talk about that in a bit. How much of this gastric juice are we producing? 2 to 3 liters. 2 to 3 liters. So if we have 1.5 liters of saliva, we have now 3 liters of gastric juice per day. We now are accounting for almost 5 liters in one day worth of fluid. So in this process, I mentioned that the gastric juices contain quite a bit of hydrogen ions. Those hydrogen ions can come in and irritate the columnar cells. Here you can see those surface, the simple columnar epithelial cells. They can come in and start attacking those cells. So to counter that, those surface mucus cells, as well as the mucus neck cells, produce a bunch of mucin. And that mucin, once mixed with the water, creates this very thick layer of mucus. And that mucus separates the pH of 2 in the lumen with that of the surrounding tissues, which should be neutral at pH of 7. So this is fairly important when we look at how we maintain the external environment, in the acidic environment in the stomach, separate from that of the tissues. Because what would happen if we don't get the production of mucus? Well, those hydrogen ions can come in and start irritating those areas. And once they start irritating those areas, they can start attacking the cells, they can start attacking the submucosal layers, which are heavily rich in nerve fibers. That absence of mucus, or that irritation of the submucosal layers, are exactly what ulcers are. Ulcers are the breakdown of the epithelial tissue, exposing the submucosal layers and irritation of those areas. So looking at that, we mentioned that there's an acidic environment of the stomach, a pH of 2. Why is this important? Well, anything that you ever end up swallowing, if you think about any lower respiratory diseases of any kind, you've got pneumonia or anything like that, you're coughing up stuff. What do you typically do when you cough it up? If you're not spitting out, you're swallowing it. And if you end up swallowing it, why do we end up swallowing it? You're still inside your human body, but that acidic environment comes in and starts destroying those bacteria. The second thing we also see is the denaturing of the proteins. So those proteins that are present in the food start to unravel and they start to separate due to those hydrogen ions. Inactivation of salivary amylase. We're stopping amylase. We're stopping the breakdown of starches due to salivary amylase. We're activating lingual lipase, and we're converting pepsinogen into pepsin. So as I mentioned earlier, we have our gastric pits. We've got our mucus layer. We have pepsinogen that's produced, again, our pepsinogen produced by our chief cells. Our chief cells are going to come in, so here's our chief cell. And that's producing our pepsinogen. Pepsinogen is going to make its way through out into the lumen of the stomach, where the pH of 2 will trim off that excess amino acids and convert that pepsinogen into pepsin. And pepsin is now an active protease. And due to the presence of that mucus, that pepsin cannot come back and break apart the proteins of those columnar cells. It's a way of keeping it separate. The other enzymes, which you mentioned, gastric lipase, intrinsic factor, IF. Intrinsic factor is needed for the absorption of vitamin B12. Vitamin B12 is important for red blood cell production. The other thing I want to also point out, the hormones, gastrin, which we mentioned for the purposes of producing gastric acid, cholecystokinin, another hormone that's also produced that will signal the production of bile by the pancreas, as well as the storage by the gallbladder. And then secretin for bicarbonate, for the production of bicarbonate and the secretion of bicarbonate to buffer that. So once we make its way from the stomach to the liver, stomach to the small intestine, the buffering that takes place from the pH of 2 comes in with bicarbonate, and then we can neutralize the acids to bring us back to the normal environment. So if I were to take us back to that earlier slide where we look at what's taking place in, I don't know how far back we have to go. There we go. Once we make it from the stomach down to the small intestine, we want to be able to buffer that through secretin. Another thing I also want to mention, what's also taking place in the stomach, is on the next slide over. On the next slide over, what's taking place, and this is just going to show us the negative feedback loop that takes place, is food entering the stomach. So food entering the stomach where we have a pH of 2. And there's two things that are happening from a mechanical standpoint as well as a physical standpoint. The physical standpoint is that the stomach expands, and there's stretch receptors that's letting stretch receptors that are receiving the stretch of the stomach, and that's all going to feed back into the submucosal plexus. So within the submucosal plexus, the ones that parasympathetic pathways innervate is going to now. So this is our control center. And our receptors, the afferent pathway, are the stretch receptors that lead into the control center. Then the submucosal plexus will then send impulses that will result in the secretion of HCl. So the efferent pathway is a production of hydrochloric acid by their parietal cells. That'll also cause local contractions or mixing waves. To start churning through, okay? So play that back one more time. The presence of food in the stomach, which will expand the stomach, will then cause the production of acids as well as contractions taking place. So that's what's happening with the physical level, with the stretch receptors. The other thing that's taking place is through the chemical changes, namely the pH. Now you've got this stomach. I'm just going to draw a stomach. And here's our esophagus. We know that the pH is a pH of 2. And whatever we're swallowing down has about a pH of 6, 6.5. Now whatever you just eat, once it makes its way into the stomach juices, what's happening to the pH as it starts to fill up? pH is going to rise. So if I have a normally acidic environment, and I start dumping, let's just say water, I start dumping, what I'm doing to that pH, or in other words, what I'm doing to that concentration of hydrogen ions, is I'm now diluting it. Right? I'm starting to fill up that stomach with water and food. Now the pH in the stomach is going to rise. And we have chemoreceptors that will detect the changes in the pH. Or in other words, detect the changes in the concentration of hydrogen ions with that of the entire volume. So the chemoreceptors detect the changes, and therefore again, lend that back to the control center, which will signal the production of hydrochloric acid. So the rise in pH, to sum that all up, the rise in pH detected by the chemoreceptors will trigger the submucosal plexus, which will then trigger it through the efferent pathway to produce hydrochloric acid by virtue of our parietal cells, to raise pH, to lower pH back down. So the rise in pH results in the lowering of the pH back to a pH of 2. What happens when we start producing enough hydrochloric acid? Once our pH runs right around 2, that's going to provide negative feedback to prevent the production of gastric juices, hydrochloric acid. So looking at that, at the stomach, as I mentioned earlier, the stomach is primarily digestion. And very little absorption actually taking place. But what type of absorption does take place? Water. Ions, some short-chain fatty acids, and alcohol. If you ever, like, I'm sure after finals, I don't know, for those of you that drink alcohol, might take that first sip of alcohol, and you might notice that all of a sudden, maybe this is just me, but I feel it within like 10-15 seconds. How does it make its way through? How do you absorb it so quickly? Well, not only are you absorbing in the mouth, there's a little bit of absorption taking place in the mouth due to the rich capillary beds there, but also absorption that's taking place within the stomach. Also, looking at water, and then combine that with some ions. What type of slurry have we seen that has water with ions in it? Gatorade is a good example. You have sodium chloride, which is salt. You have potassium in there. That actually increases the rate of water absorption. So that all takes place in the stomach. Now, where other drugs that come into play, aspirin also is absorbed in the stomach. That's a place where you can absorb fairly quickly. Now, when you filled up that stomach, and again, thinking about what happens after a large meal, after you've eaten your meal, think about the rate at which you empty out your stomach. Anytime you eat just something sugary, let's say for breakfast, you had something healthy like a donut. I was going to use a donut. What's something sugary that you can eat for breakfast? Cereal?
Frosted Flakes.
Bread, Frosted Flakes, mainly high in sugar. Do you ever feel full off that? You might feel, I mean, if you ate a bunch of Frosted Flakes, you might feel full, but you might start feeling hungry again a little bit later. Why is that? Because carbohydrates don't spend that much time in the stomach. Now, take that meal and start adding some protein to it, and that might keep you fuller a little bit longer. Why? Because it takes a little bit longer to empty that protein out of the stomach. And now add something like fats. So take a very fatty meal, and it just sits, and you feel that feeling of sitting in your stomach for quite some time. So eat something like, it reminds me of I had a contest with my friends back in college of who could eat the most ribs from Tony Roma's, because they had, like, it was like Thursday, like eat all you can eat ribs. You had like 4 big guys that came in, and you could see like the waiters are just like, oh no. It was disgusting. It's really disgusting. Anyway, the point is a lot of protein and a lot of fat after eating a gross amount of like 150 ribs or something like that. I never felt full I've never felt that full for that long before. I think it was like a full-on like day and a half I couldn't eat, and like still feeling full the next day. Why? Because it sits there in the stomach. It takes a long time. I mean, you're not only do you have a bunch of protein in there, a lot of fat, a lot of stomach motions that are the mixing waves that are taking place, and then also the the rate of gastric emptying that takes place due to the density of the food itself. Excuse me. I think it's my mouth telling me I'm done talking. All right, I got a couple more slides. So looking at the time, the gastric emptying that takes place, that's all governed by the pyloric sphincter, which is going to allow the quick squeezing of chyme into the small intestine. So in that process, we're going to start to navigate and move towards the process of digestion that takes place in the intestinal phase. So in this process, which we'll learn on Thursday, is everything that takes place with the small intestine. We're going to get pancreatic juice, we're going to get bile, and we're going to get all the other secreted enzymes that are going to dump into the small intestine. And this is how we continue digestion, again, especially within the first beginning, the duodenum, which is going to be the first 12 inches of the stomach. And if you look at the term duodenum, that's going to refer to, I believe that was 12 finger widths or something like that that you mentioned. It's actually the first 10 to 12 inches of the small intestine. So with that, you'll see the rate of stomach emptying, how we empty stuff out. And again, another thing we can look at is the rate of stomach filling. So with that, to kind of answer the question that we mentioned, that I heard a little bit earlier, is the different surgical interventions in reducing the capacity of the stomach itself. So we have different surgical interventions that have taken place. and some of them are more of the primitive ways. But the first one of it is called stomach stapling. Have you guys heard of stomach stapling? Yeah, this is actually one of the earlier ways of creating a very small pouch of the stomach. Now that you've learned the processes in which the stomach expands and signals the feeling of fullness, which we call satiety, the theory behind these surgical interventions is that if we reduce the size of the stomach pouch, you still get the stretch signals that take place that should still give you the feeling of fullness. But at the same time, if we could also limit the size, the capacity to distend or to expand, that also should give us the feeling of fullness. So what they've done in what's called vertical banded gastroplastic surgery is to staple down everything from the fundus all the way down to the mid-body of the stomach. Okay? So they create a hole, and they staple all around, and they staple up to this area, and then they create a band. They use a band around this area to limit the rate of food entering the pylorus as well as the lower body of the stomach. So as this distends a little bit, this is going to reduce the capacity of which they can consume, and then this is going to undergo the same process of gastric emptying. The next process is what's called Roux-en-Y type gastric bypass. Now, if you haven't heard of stomach stapling, have you guys ever heard of gastric bypass? Gastric bypass is actually the most invasive in all of them. And it's called Roux-en-Y. And what does Roux mean? R-O-U-X? It's a false limb. And basically what we're doing is we're completely excising the cardiac region of the stomach. And they're going to literally cut that entire thing off. They're going to separate the stomach from the esophagus. And what they'll do is they'll take now the jejunum, just downstream of the duodenum. They're going to take it, they're going to cut this area off, and they're going to attach that to this fake pouch that they've created. Hence the term fake limb. They're taking the jejunum and attaching it back to the stomach. So why do they do this? Again, smaller pouch. But then the question is, why don't they remove the rest of the stomach? Well, you can't really do that because you got a lot of arteries and veins and everything else. So you want to keep that intact. So all of this is bypassed, hence gastric bypass. You're actually bypassing the entire stomach. And you can't really cut off the duodenum because you've got all these other pancreatic pathways, which we'll learn later on, pancreatic pathways that dump into the duodenum. So anything that makes its way in here will make its way and dump right back into the jejunum. So they create, they'll section this entire area off, they break this part off, and they attach it to the stomach. And then they create a little anastomosis, a little portal that allows those pancreatic juices to dump back into the jejunum. So in effect, what this does, it limits the size of the packet and also spends less time in digestion within the duodenum. And with that, I have, let me show you the last one. I still have more? I'll talk about that later. I've got the last one, which I'll talk about. The last is called the last of the surgical intervention, and I got a video that I'll top off to show you the gastric bypass, is the lap band. Have you guys heard of this one? Yeah, lap band. It's probably all over the news. You probably say this has been around for quite some time. The lap band is a less invasive surgery in which they can use laparoscopic surgery. It's basically tubes that go in. They can create very small incisions to go into the stomach and install a port right underneath the skin, which attaches to the gastric band, an inflatable cuff that wraps around the cardiac region. And that port, so that band, again, limits the rate at which the stomach fills. So this fake pouch that's created is the area that will store the food, and it'll eventually squeeze through and make its way into the rest of the stomach. So the theory behind this is not to cut anything apart, but it's to slow the rate at which we can fill the stomach, to give you the feeling again of satiety. So with this, typically when they create this intervention, they typically want to find to see, like any type of disease or anything like that, they want to see if the typical things like diet and exercise don't work. And they would, before ever giving you the lap band, well, you'll have to have evidence that the typical conventions haven't worked to reduce your body mass index, which I won't really get into, but it's basically reducing your weight. Now the problems with the lap band is that obviously you've got a port that's installed right underneath the skin. It's not a permanent solution. People can typically report pain on the area where the band is at. You can also cause the esophagus to dilate. So typically people that have the lap band, now you've got all this excess pressure in the stomach pouch, which is going to exert more pressure on the lower esophageal sphincter. So typically people that do get the lap band can report higher rates of heartburn. So it's typically an adverse event that's expected. Another thing too is you can also get slippage of the gastric band. If that gastric band slips right back onto the esophagus, now your stomach is back to normal where it's at, and now you've got this band right around the sphincter. It can cause a lot of uncomfortability at that point. So with that, I'm going to leave you with the video. So if you are a little iffy at watching these videos, but if you are, feel free to leave, or if you just want to leave. But if you really want to just also watch how this takes place, it's a 9-minute video. I'm just going to cut to the juicy parts. And
Is this reversible?
Yeah.
gastric bypass?
Wait, lap band?
Lap band, yes. Gastric bypass, no. You'll see what they're doing right here. They're right there at the cardiac region, and they literally use this device. This device actually is really interesting because it's basically a heated wand that opens up like scissors, and then it clamps down, and it creates the scissoring motion where it will sew at the same time. So not only does it cauterize, but it also creates the stitches. So whoever created this particular device, incredible. Like a millionaire by now. So you see the excisions that take place. So now they've excised this whole area off.
Next, we're going to go down below.
Here you can see the layers of fat. They actually call now the mesentery. It's actually now considered an organ. They just named it an organ. Here they're going through and measuring the small intestine. They're going to make a cut the jejunum from the duodenum.
And then we make another division in what's called the mesentery. The mesentery is this yellow fatty tissue that we're cutting.
They used to think that mesentery was just fat, but now they called it an endocrine tissue, or an endocrine organ. There it is.
Sometimes one of those blood vessels can bleed.
So they're cauterizing.
Now we're going to start to run the small intestine so that we can find the intestine back to
That's
itself.
plumbing. They're glorified plumbers. Like orthopedics, glorified carpenters.
And we'll start construction.
That's a mouthful. Jejunostome.
First step is to make a hole.
It's basically sticking two pieces together. They create a hole, stick them together,
The second hole in the other part of the small intestine.
and
And this time we're going to put our finger
so this is the
inside
anastomosis, the hole that they're creating between the two.
so that we
The
can
jejunum attached to the jejunum, just downstream from the duodenum.
recall that the last time we stapled on the outside of the intestine to a split valve. Now we're putting the staple inside.
And then they're gonna seal this all the way around. And watch as the device works. They've now sealed it together,
Now we still have a resultant hole here.
and now they're gonna take that and they're gonna clamp
So
it.
we're going to take our stapler one more time and close that hole. And now we have completed our jejunostomy.
So now they've connected the two.
Click that file, and you'll notice that there is a defect here behind the file.
So when I get to the later part, what do plumbers do when they want to detect leaks?
See that hole right there?
Fill it up with water, which is exactly what they do. So they'll fill this whole area up with water. This is just kind of fixing a defect here. They're going to fill this whole area up with water, and they're going to push a bunch of air through to see if there's any leaks. What are they doing?
Pouch.
Oh no, they're still creating the pouch.
Pouch.
Here's the pouch that they're creating.
This extra tissue is hanging on by a thread, so we'll just use one more fire with the stapler to remove it.
See how the stapler works? Zip it up.
And now our gastrojejunostomy is completed.
So that's it. That's a gastric bypass. They created the pouch. Everything's stuck together now. You're going to keep the stomach in place.
There's just one more of those mesenteric defects right here.
And
Air bubbles.
so look, they filled it up with water,
Air bubbles within the
and they're filling up. They're basically blasting air down into the stomach, and just checking for any leaks.
air bubbles. So you know that the connection is airtight.
That light that you're seeing is a laparoscope that's on the inside. That's all it is, plumbing.
Now we simply suck out all of our water. And
All right, thanks for sticking through. I will see you guys on Tuesday for a short week.
And our operation is complete.